In this example problem, we see various scenarios where we have a box on its surface. And we're going to apply Newton's second law to determine the accelerations, the forces, the mass, all the elements related to this box. So I'm going to work through one by one each of these different scenarios. Again, these are kind of like 6 or 7, 8 different problems or little mini parts. I'm going to work through them one by one. But we start with the statement that a 33 kilogram box rests on a flat surface. And A and B and C kind of relate to that scenario. So right under here, I've got all my equations that I'm going to use for this unit. We have Newton's second law, which is our F equals ma, and then a bunch of our impulse equations here where we're going to relate momentum concepts to Newton's laws. But let's look at scenario A, and I'm just going to draw the box, and I'm going to draw the surface, right? And here we have what we call a free body diagram, right? So if this box is at rest, then off to the side, again, not part of my free body diagram, but it's important to identify some things. I like to identify that there's no velocity. More importantly, we know that there is no acceleration. That's what really matters here with a free body diagram is the object accelerating, right? And if it's not accelerating, then therefore the net force, the sum of the forces has to be 0. Right, so when I'm drawing the free body diagram of this box at rest on a flat surface, I know that all the forces better cancel out. So let's draw the forces. Well, the first force is going to be Fg, straight down. Right? That is the force due to gravity. And there must be something that is balancing that force. And that's going to be the surface. We call that the normal force. We can draw this normal force 2 places. You can draw it here as an upward force acting on the box. Or if you prefer, you're welcome to draw it down on the bottom acting up. Either way, the arrow points upward and is equal in magnitude, the same length, as the force of gravity, Fg, and it's upward, right? So it's going to cancel out the force of gravity, right? So you have 2 forces acting on this box. Inside the box, I might even identify that it is 33 kilograms. That could be helpful information, right? So that's identifying the mass of the object. So let's start answering the questions. Well, they gave us something in kilograms, and so I know my mass is 33 kilograms. But what is the weight? Well, weight is the same as the force due to gravity, right? So Fg is also known as the force of weight, or just weight. And what is Fg? How would you evaluate that? Well, what if this box did not have the surface underneath it? What would Fg do? Well, if it did not have the surface, the force of gravity would be the only force, and F equals ma suggests that it would be accelerating. Well, in this case, since it would be accelerating due to gravity, we know that the mass would be accelerating due to gravity. F equals m times a. If it's the only force, we're in free fall. And ag is simply downward at 9.8 meters per second squared on Earth. The mass we know is 33 kilograms. And so if I wanted the weight, I'm always just going to take the mass of the object and multiply it by the acceleration due to gravity on that planet. And oftentimes that's going to be Earth, right? So if I take 33 and multiply by 9.8, I get the weight. 323.4 is what Fg is. The force due to gravity is 323.4, and that is in newtons, right? Forces are always in newtons. Now, remember, a newton is a kilogram times a meter per second squared, right? So we're just going to write it as newtons. So I'm going to write in here that it is 323.4 newtons. So oftentimes when we solve a forces problem, they're either going to give you the mass and they're going to ask you to find the weight, or you're going to need to find the weight, or they might give you the weight and you'll need to determine the mass of the object by, spoiler alert, dividing by 9.8. So if I wanted the mass is always going to be equal to the force of gravity divided by the acceleration due to gravity. All right, so these are important things to know that are going to be true for every dynamics problem. If they give you the mass, you can find the weight, Fg. If they give you the weight, Fg, you can divide by 9.8 to get the mass. So in this case, they gave you the mass, we find Fg. Well, then what is the normal force? Well, as we see in our free body diagram, the normal force is the only other force acting on this box. We have no motion, there's no acceleration, there's no friction because we're not moving, there's no external force other than those two. And so since it has to balance, then the normal force is going to be the same amount as gravity and upward. So I'm going to say the amount is 323.4 newtons. That is what the normal force is. Now, If I asked you what direction, it would certainly be up and gravity would be down. So there could be a sign component. If I just say how much force, I'm just asking you how long is the arrow. So I would say the answer for both of those are the same values. All right, so let's move on to D. Well, now it says, what would the net force be on the box if it's accelerating? Well, that's a different scenario now. So I'm going to redraw my free body diagram, D. I'm going to draw the box, and I'm going to give it an acceleration. I'm going to look over to my right, and I'm going to say, well, it could be moving or not moving, but it is accelerating. Let's say it's accelerating to the right. All right, if it's accelerating to the right, therefore, there must be a net force, F net, also, that is also to the right. F net is the same as the net force, sum of the forces. All right, so they actually didn't tell you how it's getting this net force. It could be an applied force to the right, right? It might be some kind of tension pulling to the right. We don't actually know what the force is on this free body diagram. This object likely has a gravitational force and a normal force, but it's accelerating, right? So you're probably going to get some kind of applied force to the right. You might even have some friction on there. We don't know what those forces are, but we do know that the sum of all of those forces, the sum of the forces is equal to some unknown amount, and that's what they're looking for. However, our equation for Newton's second law says that F equals ma. So if we know the mass and we know the acceleration, we could evaluate that, right? So we're going to label, just like we've done in the past, all of our variables that we could have. The net force we don't know, but we do know it's accelerating. I just decided to put it to the right at 2.2 meters per second squared. The box still has a mass of 33 kilograms. And so if I want to evaluate the net force, I'm just going to take m times a. In this case, it's going to be 33 times 2.2. And I'll just pull out my calculator. 33 times 2.2. And you get 72.6 newtons as the net force. All right, so again, we actually don't know which forces are causing that acceleration. We just know that there is some amount of leftover or unbalanced amount of force, this tug of war of forces that could exist. The winner is winning by 72, and that's causing that acceleration. All right, so let's move on to the next scenario. Now it's asking how much mass has been added to the box if this same force causes an acceleration of just 1.7. Well, if you have the same net force, but less acceleration, well, then we know there must be a changed mass. So I'm going to label my variables again. We have the net force, we now know is 72.6 newtons. What we don't know is this new mass. There is a new mass associated with it. And the new acceleration is less. It's only 1.7 meters per second squared. And so I can find the new mass. Now, just knowing what I know, if the acceleration goes down for the same amount of mass, well, then I know that the mass overall has had to have gone up, right? But I can evaluate it. The net force is equal to m times a. I can rewrite that to solve for m. M is the net force over the acceleration, which would be 72.6 newtons divided by 1.7 meters per second squared. So I'm going to evaluate that, divide by 1.7. And I'm going to get that it's now 42.7 kilograms. That is the new mass of the object. And so I'm going to look to put in my answer, and I'm going to reread the question. How much mass has been added? Be careful, right? Our answer is not 42.7. How much mass is added? Well, we need to subtract the original mass from there. So 42.7 kilograms minus the 33 kilograms, which is our original mass. And I'm going to get about 10 minus 33. And that would be 9.7 kilograms has been added, right? So be careful to read the equation so you know what they're asking for, right? We found the new mass, but they want to know how much was added. So I'm going to put 9.7 kilograms. So you're starting to see how these problems might be worded in these basic scenarios. All right, let's look at scenario F. The original box slides along the surface and experiences a frictional force of 39 newtons. How much applied force would be required for the box to slide at constant velocity? All right, so I hope you recognize this is, again, a new scenario. These are new forces. It is the original box, so we do know the mass. So I'm going to start, as we do with any problem here. I'm going to label F And I'm going to start once again with a free body diagram. So there's the box, right? It's 33 kilograms, the original box. What do we know? It slides along the surface and experiences a frictional force. All right, so I'm going to draw my free body diagrams. I know that I have gravity acting straight down, Fg. I have a normal force acting straight up, Fn. We have no indication of any other up or down forces. Off to the side, just for my own thinking, I'm going to identify and say that it is moving to the right. All right, I'm just going to identify motion to the right. This is not part of my free body diagram. This is just for my own thinking, because I need to evaluate, are we accelerating? Well, they tell you it's moving at constant velocity, which tells us something about the acceleration. The velocity is not changing. That means that A is equal to 0 meters per second squared. And therefore, if we're not accelerating, the net force has to be 0. Well, all right. Well, I do know there is another force on there, and they tell us that's going to be friction. And friction opposes motion. If I have it moving to the right, friction is going to be to the left. That's the force of friction. And so if I'm at constant velocity, well, there must be one other force. Something is pulling to the right. And that's something I'm going to call the applied force. And since I'm not accelerating, the net force has to be 0. My up and down forces cancel. Well, that means Fa has to be equal to the friction force. They have to be the same amount. Another way to write that would be that the sum of the forces, and we're going to separate this out. I'm going to say that we have an X and a Y direction. We're going to see this happening later. We really have motion in the X direction, so I'm going to only consider the X forces, and those cause that mass to accelerate in the X. And so if I sum the forces, if I add the applied force and the friction force, the sum of the forces would cause the mass to accelerate in the X. So it's another way to write Newton's second law is to put all the forces on the left side. And then I'm going to type right in the values. Well, I have Fa plus, and here's where that direction comes into play. Friction is left at 39 newtons, right? It's a left arrow, so I can put it in there that way. And the mass is 33, but my acceleration is 0, so that all goes away. And you get that the applied force must be positive 39 newtons. Well, of course, that's what our free body diagram says. So again, in this case, we didn't need to truly calculate that, but I'm showing you mathematically how we get to that value, right? Those two forces have to cancel each other out. So I know that in this case, you must have an applied force of 39 newtons to balance the friction force because it's at constant velocity. All right, last one. The applied force has been increased, but the friction remains the same. So this thing's already sliding. We have this friction force, but now we have more applied force than 39. Well, what's going to happen? Well, let's draw this free body diagram. All right, we have the same box on a surface. We still have gravity acting down, Fg. We still have a normal force acting straight up, balancing Fg. We have the same friction that is left. That's our force of friction. And now we have a new applied force, but it's gotten bigger. I'm going to draw a bigger arrow, Fa. All right, and I'm going to evaluate and figure out that we're going to have a new acceleration. All right, this thing is going to be accelerating to the right due to the imbalance of forces. The net force is going to be to the right in this case. Right, so I'm going to label what I have. And really, again, Fg and Fn. Sorry, I miswrote my Fn here. That should be an N. Those are going to cancel. What we really care about are these forces that act left and right, or in the X direction. We can set up our table of values. We know that the sum of the forces has to equal m times a. And so let's figure out, we know what mass is. It's 33 kilograms. I'm going to set up my variables. A in the X direction is what we don't know. We're going to figure out what that is now. I'm going to put a little blank here. I'm just setting up a table of knowns. We know that it has an applied force. And in the problem, they tell you now this applied force has been increased. So now it is 74 newtons. I have an arrow that I drew to the right, so I'm going to put plus 74 newtons. And then my friction force has remained the same. The force of friction is still the same amount. It was 39, and it's left 39 newtons. So again, getting these signs are important because forces are vector values, right? And again, we have 4 variables here, 1 unknown, and I'm going to set up my equation here. I know that the applied force plus the friction force, again, I'm adding vectors, is equal to the mass times that acceleration that happens to be in the x direction. And I'm going to plug in the values I know, right? Positive 74 plus, I'm adding a vector. Well, I can add negative numbers, 39. So I'm really subtracting 39 is equal to 33 times the acceleration in the x. And we could solve for a, right? So on the left side, if I take 74 and I add a negative 39, which is really subtracting 39, I get a net force of 35. The net force is 35 newtons. That is the net force. And that is equal to 33 times A. And if I divide both sides by 33 to isolate A, I get A is equal to 1.06. A is equal to positive 1.06 meters per second squared. It is a positive value, which is what I expect based on how I drew my picture. And I'm going to write it in my box. So I get 1.06. All right, so here we see the application of multiple example problems, really basic ones, introducing us to how we're going to use Newton's second law, which is just F equals m times A, to look at all the forces on an object in a free body diagram, set up the variables that I know, be careful with direction and signs. In all of these problems, any acceleration was only in the x direction, but we could see accelerations vertically as well, and really evaluate to find those missing pieces. So hopefully this gives you a good introduction to how we're going to set up and solve problems, and some of the basic concepts that we're going to use.